engineering students, right? Dear students, welcome to the ACE Engineering Academy online platform. I am Malakondaiah Gandham, thermal faculty in our academy. I have more than 25 years of experience in the teaching field. In this session, we are going to discuss the syllabus from thermal engineering and the most important questions from the thermal engineering. Okay, first let us take the syllabus. The syllabus for SSC JE from thermal engineering is basics of thermodynamics, applied thermodynamics, power plant engineering, IC engines. This is the syllabus for the SSC JE mechanical engineering under the thermal engineering. Then here we are dividing, I am dividing this entire syllabus into two parts. Today we are going to discuss the syllabus and the most expected questions from the first part, that is basics of thermodynamics and applied thermodynamics. Okay, in the other session we will have another session where we are discussing the syllabus and the most expected questions from the power plant engineering and IC engines. As we all know, this is the highly weightage subject. The weightage varying from 45 marks to 55 marks. That means on an average you can expect 50 marks only from thermal engineering. Okay, that is the weightage of this thermal engineering. Okay, now let us see the syllabus for the basic thermodynamics, basics of thermodynamics, heat and work, first law of thermodynamics, second law of thermodynamics, entropy, availability and properties of pure substances. This is the syllabus under the basic thermodynamics. Similarly, look at the syllabus under the applied thermodynamics, air cycles, also called gas power cycles, gas turbine cycles, Rankine cycles and refrigeration. This is the syllabus under applied thermodynamics. Dear friends, remember, from basic thermodynamics and applied thermodynamics, the weightage is around 25 marks. The number of marks are varying from 20 to 25 only from basic thermodynamics and applied thermodynamics. That is the weightage of these two topics. Okay. Now let us take the very important questions from the basic thermodynamics and applied thermodynamics. Okay, look at the very first question. It is asked like this: a closed gaseous system undergoes a reversible constant pressure process. That constant pressure is given 2 bar. The constant pressure P equal to 2 bar. You know 1 bar equal to 100 kilopascal. It is equivalent to 200 kilopascal. 1 bar equal to 100 kilopascal. Kilopascal or kilonewton per meter square, in which 100 kilojoules of heat is rejected. The amount of heat rejection is 100 kilojoules. Thermodynamically, heat supplied is taken as positive, heat rejection should be taken as negative. Since it is a rejected heat should be marked with a negative sign. Okay, it is like this. Let this is your system. If the heat is entering to the system, that kind of heat is taken as positive heat. Similarly, if the system is losing the energy, heat energy, the heat is transferring from system to surroundings, that kind of heat is taken as negative heat. Since it is given heat rejection, that is 100 kilojoules with a negative sign, and the volume changes from 0.2 meter cube to 0.1 meter cube, the initial volume V1 0.2 meter cube and final volume V2 equal to 0.1 meter cube. 0.1 meter cube. The change in internal energy of the system is, you are asked to decide the change in internal energy of the system. It is clearly given the problem connected to closed system. As you know, the closed system energy balance equation is Q equal to W plus du. W plus du. Right, from this, the change in internal energy du equal to Q minus W. Heat transfer minus W. But work done for a closed system is integral 1 to 2 PdV. This is the closed system work. Is also called non-flow work. Since it is given constant pressure process, right, at constant pressure you can write P outside, integral dV, V, apply the limits from 1 to 2, it is becoming V2 minus V1. It is equal to P, look at the P value, 200 kilopascal, 200 into 0.2 V2, what is the V2 value? 0.1, should be very careful. Right, 0.1 minus 0.2, 0.1 minus 0.2, it is equal to 200 into minus 0.1, simplify it for getting minus 20 kilojoules. That is the thermodynamic work for a closed system. Right? Then what is the change in internal energy? Heat transfer minus W. Heat transfer is given minus 100 kilojoules. Minus 100 minus work done itself is minus 20. It is equal to minus 100 minus of minus plus 20. Minus 100 plus 20 is equal to minus 80 kilojoules. That is the thermodynamic heat transfer. Okay. Now look at the options. Option B is absolutely correct. Is it clearly understood? This is the most expected question, most important question, right? Similarly, look at the another important question. It is asked like this. One reversible heat engine operates between 1600 Kelvin and T2 Kelvin. Let me draw the diagram. One reversible heat engine cycle operating between temperature limits T1 given 1600 Kelvin and T2. This is the another reservoir where the heat is rejected at T2 temperature. Okay. Here this source is supplying the Q1 amount of heat. A part of the heat energy is converted to work energy. The remaining heat energy is dumped to the cold source. The magnitude of heat dumped to the cold source, that is intermediate source, is Q2. Then, and another reversible heat engine operates between T2 Kelvin and 400 Kelvin. Another reversible heat engine, this is the another reversible heat engine. Then I can say this is the reversible heat engine 1, reversible heat engine 2. This reversible heat engine 2 is receiving or operating between T2 Kelvin and another temperature 400 Kelvin. That means second reversible heat engine operating between temperature limits T2 and another source temperature is given 400 Kelvin. This is the T3 equal to 400 Kelvin. This reversible heat engine 2 is receiving Q2 amount of heat energy. A part of that Q2 is converted to work energy. The remaining heat energy is dumped to the cold source. The magnitude of heat dumping is Q3. That means indirectly, two reversible heat engines are arranged in series such that the heat rejected by the first reversible heat engine is equal to heat received by the second reversible heat engine. Okay, that is the arrangement for the given data. if both engines have the same heat input and output. Both heat engines are having same heat input and output. That means output of the reversible heat engine 1 is equal to output of the reversible heat engine 2. Similarly, the heat in for what is given, if both heat engines have the same heat input and output, heat input for reversible heat engine is equal to heat input for reversible heat engine 2. Then what is the efficiency? You know, efficiency equal to output by heat input only. Since output of the both engines remaining same, heat input also remaining same, indirectly I can say that efficiency of the first reversible heat engine is equal to efficiency of the second reversible heat engine. Okay, understood clearly? Yes. Then you know, reversible heat engine efficiency when it is operating between the two temperature limits, reversible heat engine efficiency when it is operating between the two temperature limits is 1 minus minimum temperature dividing by maximum temperature. Okay, here according to given condition, efficiency of the reversible heat engine 1 is equal to efficiency of the reversible heat engine 2. It means 1 minus T minimum by T maximum for the reversible heat engine 1 is equal to 1 minus T minimum by T maximum for the reversible heat engine 2. You know, reversible heat engine 1 is operating between 1600 Kelvin and T2. That means that T2 is the minimum temperature for the reversible heat engine 1 minus T2 by 1600 Kelvin is equal to 1 minus for the reversible heat engine 2, T3 is the minimum temperature, 400 divided by maximum temperature for the reversible heat engine 2 is T2. Simplify this value, right, for getting the answer. So it is indirectly T2 by 1600 is equal to 400 dividing by T2, or T2 square is equal to 1600 into 400. You simplify this value for getting the answer. T2 equal to root under 1600 into 400, it gives 800 Kelvin. That is the intermediate source temperature. This T2 equal to 800 Kelvin. That is the answer. Okay, look at the answer. Option D is absolutely correct. It is also the very important question. I can say that 5-star question. 5-star question means most expected question for competitive exams like SSC, JE. Similarly, look at the another important question. It is asked like this: in which one of the following situations the entropy change will be negative? You are asked to decide the situation where the entropy change is negative. Okay, look at the option A. Air expands isothermally from 6 bar to 3 bar. Right? You know, the change in entropy at constant temperature. Isothermal means constant temperature. Equal to what? Mr ln V2 by V1. Okay? At constant temperature, according to Boyle's law, P1 V1 equal to P2 V2. From this I can write that P1 by P2 is equal to V2 by V1. In place of V2 by V1, I can write P1 by P2 Mr ln P1 by P2. P1 by P2. Look at the P1 and P2. P1 is 6 bar, P2 is 3 bar. That means this is 6 bar and this is the 3 bar. 6 by 3 equal to 2. ln 2, ln greater than 1 always positive. Therefore, it is greater than 0 means entropy is going to increase with the first situation. But you are asked to decide the entropy change should be negative situation. The situation should be decreasing the entropy of the system. Look at the option B. Air is compressed half the volume at constant pressure. Right? Option B, this is option A. B, change in entropy at constant pressure. Change in entropy at constant pressure. The change in entropy at constant pressure equal to what? Del Q at constant pressure dividing by temperature. Del Q at constant pressure mcp dt dividing by T. For getting the total change in entropy, integrate and apply the limits for getting mcp ln T2 by T1. That means you need to integrate and apply the limits for getting the total change in entropy. Right? It is the change in entropy formula at constant pressure. But at constant pressure, volume is directly proportional to temperature according to Charles' law or constant pressure law. Now, here, since volume is directly proportional to temperature, I can say that V2 by V1 is equal to T2 by T1. So, this T2 by T1, mcp ln, this T2 by T1 I can also write V2 by V1. Now, look at the statement. Air is compressed to half the volume at constant pressure. That means it is given V2 equal to V1 by 2. If V2 equal to V1 by 2, this quantity is becoming half. 1 by 2 means 0.5, which is less than 1. ln fractional value always negative. Since ln fractional value always negative, ln 0.5 is negative value, here the change in entropy ds at constant pressure is negative. So, option B is the situation where the change in entropy is negative. Therefore, option B is absolutely correct. Understood clearly? Now, look at the third statement. Heat is supplied to air at constant volume till the pressure becomes 3 folds. Here, at constant volume, the ds at constant volume equal to del Q at constant volume dividing by temperature. Here heat is supplied. This Q, del Q itself is positive. Right? Therefore, since del Q itself is positive, the change in entropy is positive with the third situation. That is not correct. Air expands isentropically. That means for this situation, the change in entropy ds equal to 0. Therefore, option B is the situation where the entropy change is negative. I hope all of you clearly following. Okay. Similarly, look at the another important question. The effects of heat transfer from a high temperature body to a low temperature body are. That means when the heat is transferring from high temperature body to low temperature body, the energy is conserved, the entropy is not conserved, the availability is not conserved. Right? It is like this. Right? Options are given. Here heat is transferring from high temperature reservoir. This is the high temperature reservoir where the temperature is T1, and this is the low temperature reservoir. Low temperature reservoir where the temperature is T2. Here heat is transferring from high temperature reservoir to low temperature reservoir. It means whatever the heat energy, the high temperature reservoir is losing, the same will be getting or obtained by low temperature reservoir. Therefore, this heat energy Q is coming under conservable quantity, that is given as statement 1. The energy is conserved. Definitely, energy is conserved. According to first law of thermodynamics also, energy neither be created nor be destroyed, but one form of energy can be converted to other kind of energy. Therefore, first statement is absolutely correct. Now look at the second statement. The entropy is not conserved. Entropy is not a conservable quantity. right? Because entropy is going to increase. Let us say this T1 equal to, for your better understanding, 1000 Kelvin, T2 equal to 500 Kelvin. The heat transfer Q equal to 2000 kilojoules. Now this heat transfer Q is coming under positive with respect to low temperature reservoir. The same fellow comes under negative with respect to high temperature reservoir, because the high temperature reservoir is losing the heat energy. Then the entropy change with respect to high temperature reservoir is equal to minus Q by T1. It is equal to minus 2000 dividing by 1000. It is equal to minus 2 kilojoules per Kelvin. Similarly, the entropy change with respect to low temperature reservoir equal to plus Q by T2, because the low temperature reservoir is receiving the heat energy. That is 2000 dividing by 500. It is equal to 4 kilojoules per Kelvin. Then what is the net change in entropy? Net change in entropy equal to change in entropy of the high temperature reservoir plus change in entropy of the low temperature reservoir. Change in entropy of the high temperature reservoir minus 2 plus low temperature reservoir 4 is equal to 2 kilojoules per Kelvin. So entropy is going to increase by the time the heat is transferring from high temperature reservoir to low temperature reservoir. That's why entropy is not coming under conservable quantity. Therefore second statement also correct. Right? Come to the third statement. The availability is not conserved. Absolutely correct. The reason is unavailable energy. Unavailable energy is equal to what? T0 into ds. Net change in entropy. This T0 is the atmospheric temperature. This T0 is generally taken as 300 Kelvin. That is the dead state temperature. 300 plus net change in entropy 2. It is equal to 600 kilojoules for our data. Anyhow, unavailable energy increases. Unavailable energy, positive means unavailable energy is going to increase. By the time the unavailable energy increases, available energy decreases. Therefore, the availability is not coming under, right, conservable quantity. First statement, second statement, third statement, all the three statements are correct. Therefore, option D is absolutely correct. Okay. Similarly, look at the another important question. It is asked like this. Which one of the following represents the condensation of a mixture of saturated liquid and saturated vapor in the enthalpy entropy diagram? Enthalpy entropy diagram means what? It is HS diagram or Malakondaiah diagram. Okay. Let us construct the HS diagram. Enthalpy versus entropy coordinate system is also called Malakondaiah diagram. The saturation dome with HS coordinate system is looking like this. The saturation dome, that is how the saturation dome is appearing with Malakondaiah diagram or HS coordinate system. One of the constant pressure line is appearing like this. The constant pressure line is almost a straight line within the saturation dome, but bending upwards in the superheated region. Okay. So that means constant pressure line is inclined line with the HS diagram within the saturation dome, but it is bending upwards in the superheated region. Remember, though it is bending, the constant pressure line is bending upwards in the superheated region, it is maintaining positive slope. It is maintaining positive slope means as the enthalpy increases, entropy also increases. Right? Then what it is given? Let me read the problem. Which one of the following represents the condensation of mixture of saturated liquid and saturated vapor? The mixture of saturated liquid, this is the saturated, saturated vapor curve, saturated vapor curve. This is the saturated liquid curve, saturated liquid curve. Within the saturation dome only, right, two-phase mixture, that is saturated vapor and saturated liquid available. This may be the initial state of the two-phase mixture. That two-phase mixture, that means saturated vapor and saturated liquid is condensing. Condensation is happening at constant pressure. The condensation may be happening like this along the constant pressure. It is a straight line, inclined line. So 1, 2, 2 I can say the condensation of the two-phase mixture, that is mixture of saturated vapor and saturated liquid. So look at the condensation. Condensation is happening, right, at constant pressure and constant temperature, that is along the constant pressure line. Therefore that line is looking like a inclined line. Look at the option, an inclined line of constant slope. Option B is absolutely correct. Is it clearly understood? Once again read the problem. Which one of the following represents the condensation of mixture of saturated liquid and saturated vapor? You know, along the saturated vapor curve only saturated vapor is available. Along the saturated liquid curve only saturated liquid is available. But it is given mixture of saturated vapor and saturated liquid. That's why the initial state I took as a wet vapor. Right? This is the wet state of the given vapor. Wet state of given vapor. Anyhow, remember, all pure substances like water, steam can maintain constant pressure and constant temperature during the phase change process like boiling, condensation, freezing, melting, sublimation and desublimation, etc. You know, the evaporation means phase change from liquid to vapor. The reverse process is called condensation. Similarly, the phase change from solid to liquid is called melting. The reverse process is called freezing. The phase change from liquid to solid is called freezing. Similarly, the direct phase change from solid to vapor is called sublimation and the reverse process is called desublimation. Dear friends, remember, the sublimation and desublimation both are happening below triple point state only. Below triple point state pressure only, right? The direct phase change from vapor to solid or solid to vapor can be happening. Remember, below the triple point state, liquid phase cannot be existing. That means below the triple point state, the material may be available either in the solid state or vapor state. Liquid phase cannot be found. Understood clearly? Yes. Then option S we have selected. Okay, once again. Right. Now let us take the another question. Look at this question. The order of values of thermal efficiencies of Otto, diesel and dual cycle when they have equal compression ratio and heat rejection. Equal compression ratio means compression ratio for Otto cycle equal to compression ratio for diesel cycle is equal to compression ratio for dual cycle. Similarly, the same heat rejection means heat rejection for Otto cycle equal to heat rejection for diesel cycle is equal to heat rejection for dual cycle. With these two conditions, you are asked to decide relation between the three cycles efficiency. For remember, before going to construct the diagram, remember the dual cycle efficiency. You know, for Otto cycle, heat is supplied at constant volume, whereas for diesel cycle, heat is supplied at constant pressure. Whereas in the dual cycle, the heat is partially supplied at constant volume, remaining part is at constant pressure. That means the heat supplied in the dual cycle in two processes, the first part of the heat supplied at constant volume, second part of the heat supplied at constant pressure. Since the heat is supplied in two processes, that's why that cycle is called dual combustion cycle. Dual combustion cycle is the combination of Otto and diesel. Therefore, the dual cycle efficiency always in between Otto cycle efficiency and diesel cycle efficiency. Having that information, let us project the TS diagram for Otto cycle and diesel cycle. Temperature versus entropy diagram. You know, Otto cycle consists of four processes. Otto cycle consists of four processes. Two are isentropic process and two are constant volume process. For Otto cycle, heat supplied and heat rejection takes place at constant volume and compression expansion taking place at constant entropy. So 1 to 2, it is the isentropic compression. I am projecting the TS diagram for Otto cycle, and 2 to 3, constant volume heat supplied. Constant volume heat supplied, let us mark that is 2 to 3. Constant volume heat supplied. 3 to 4, isentropic expansion. Similarly, 4 to 1, constant volume heat rejection. That is the Otto cycle. For Otto cycle, 1, 2, 3, 4. 1, 2, 3, 4, 1 is the Otto cycle. Otto cycle. Okay. Now let us mark the diesel cycle. For constructing the diesel cycle, conditions to be satisfied. The conditions are compression ratio for Otto cycle equal to compression ratio for diesel cycle. Diesel cycle. What is the compression process for Otto cycle? 1 to 2. Since 1 to 2 is the compression process for Otto cycle, for that compression ratio for Otto cycle must be equal to compression ratio for diesel cycle. Therefore, 1 to 2 for Otto cycle must be equal to 1 dash 2 dash for diesel cycle. Okay. And another condition is the heat rejection for Otto cycle is equal to heat rejection for diesel cycle. Look at the 4 to 1. 4 to 1 is the heat rejection for Otto cycle. But heat rejection for Otto cycle must be equal to heat rejection for diesel cycle. Therefore, that 4-1 for Otto cycle must be equal to 4 dash 1 dash for diesel cycle. Okay. Then what is the process which is deviating from the Otto cycle in the diesel cycle? 2 to 3, that is the constant volume heat supplied, right, for Otto cycle, whereas for diesel cycle we need to supply the heat at constant pressure, right. That constant pressure heat supplied curve must be drawn with a slope less than the constant volume heat addition, right, curve with a TS diagram, because the slope of the constant volume curve dt by ds at constant volume equal to T by CV, whereas dt by ds at constant pressure is T by Cp. The quantity dt by ds is the slope of constant volume curve with a TS coordinate system, right. Since the slope of the constant volume curve with the TS coordinate system is T by Cv, the T by Cv is more than T by Cp, because the Cv is always less than Cp for any gas. Therefore, I can say that the slope of the constant volume curve, right, with the TS diagram is more than the slope of the constant pressure curve. That's why I have selected the constant pressure heat addition curve for diesel cycle with less slope, that is marked as 2 dash 3 dash. Remember that 3 dash must be lying along the 3 to 4, because the heat rejection, the 4 and 4 dash both are identical for both Otto cycle and diesel cycle. Then only this 3 dash 4 dash is the isentropic expansion for having the 4 dash 1 dash heat rejection for diesel cycle. So anyhow, that 1 dash 2 dash 3 dash 4 dash 1 dash is the diesel cycle. Okay. Then what is the efficiency? You know, efficiency of any cycle equal to 1 minus heat rejection by heat supplied. Now look at the heat rejection. Heat rejection for Otto cycle equal to heat rejection for diesel cycle. That means this fellow is going to remaining same for both cycles. This fellow remaining constant. Then the cycle which is working for more heat input, right? for the same heat rejection, if heat supplied is more, then this quantity is going to decrease. 1 minus decreasing value will increase the efficiency. For that, we need to estimate the heat supplied for Otto cycle. Heat supplied for Otto cycle is area below 2,3, because 2,3 heat supplied for Otto cycle. So, right, heat supplied for Otto cycle equal to area below 2,3, because area below TS diagram is the heat transfer for a particular process. Similarly, heat supplied for diesel cycle is equal to area below 2-3 area below 2-3. From that you can conclude that area below 2-3 is less compared to area below 2,3. From that I can say that the heat supplied for Otto cycle is more compared to heat supplied for diesel cycle. The heat supplied for Otto cycle is more, definitely I can say that Otto cycle efficiency is better than diesel cycle efficiency. Once I know the relation between Otto cycle efficiency and diesel cycle efficiency, in between these two cycles I can put the efficiency of the dual cycle. Therefore, efficiency of the Otto cycle is more compared to efficiency of the dual cycle is more compared to efficiency of the diesel cycle. This is very, very important information. For the same compression ratio and heat rejection, Otto cycle efficiency is more than dual cycle efficiency more than diesel cycle efficiency. Look at the option D. Option D is absolutely correct. I hope all of you clearly understood. Is it understood or not? Yes. Then look at the another question. It is asked like this: which one of the following statements applicable to a perfect gas will also be true for irreversible process? Symbols having the usual meanings. dq equal to du plus pdv. This is for only reversible process. This is for only reversible process, because actually dq equal to del w or dw. एक minute. dq equal to dw plus du. This dw equal to pdv only for a reversible process. Since pdv is written in the place of w, that w equal to pdv for only reversible process, therefore this equation is applicable for only reversible process. But you are asked to decide, or you are asked to find the equation which is valid for both reversible process and irreversible process. dq equal to dds. You know, ds equal to del q by t only for a reversible process. Only for reversible process. Then del q equal to tds only for a reversible process. So this equation is valid for only reversible process. Look at the third one. TDS equal to du plus PdV. Look at the quantities connected to this equation. T, temperature property. S, entropy property. U, internal energy property. P, pressure property. V, volume property. That means this particular equation is maintaining only properties. Dear friends, remember, the equation which is maintaining only properties is valid for both reversible process and irreversible process, because the properties do not care the reversibilities or irreversibilities of the process. Once again, the equation which is maintaining only properties is valid for both reversible process and irreversible process. Therefore, option C is absolutely correct. Okay, that means this equation is maintaining only properties. That kind of equation is applicable for both reversible process and irreversible process. That's why I selected the option C. It is also most expected question, 5-star question, right? Similarly, look at the another question. It is asked like this: the minimum temperature to which water can be cooled in the cooling tower. Dear friends, remember, the cooling towers are used for cooling the hot water available from the condenser of the thermal power plant or refrigeration units. In the cooling tower, that water can be cooled to the wet bulb temperature of the atmospheric air only. Once again, in the cooling tower, Cooling tower is used for cooling the hot water available from condenser of the thermal power plant or condenser of the refrigeration plant. Okay. In the cooling tower, water is cooling by dumping the heat to the atmospheric air. By the time the air is receiving the heat energy from the water can be cooled up to wet bulb temperature of the atmospheric air only. Then look at the option, the wet bulb temperature of the atmospheric air. Option B is absolutely right, correct. That is very, very important point. Okay. Similarly, look at the another important question. It is asked like this. In a steam power plant, feed water heater is a heat exchanger to preheat the feed water by leave steam from the steam generator. No. Hot flue gases coming out of the boiler from furnace, absolutely wrong. Hot air from air preheater, absolutely wrong. Extracting the steam from turbine, absolutely correct. In the thermal power plant, the feed water can be reheated. The feed water can be preheated by extracting the part of the steam from the lateral stages of the turbine like this. The main parts of any thermal power plant is boiler. This is the boiler. For this boiler, water is supplied. The water which is supplied to the boiler is called feed water. This is the feed water. That feed water is becoming the steam. For thermal power plant, generally it is superheated steam. Superheated steam. That superheated steam is made to expand in the large stages of the turbine. This is the turbine. This is the turbine. This is the steam turbine. After expansion of the steam over the turbine blades, that steam is left to the condenser. That steam is left to the condenser. This may be the condenser where the coolant is available. For that coolant, this steam is dumping the heat. Then the steam is becoming liquid. That liquid is called condensate. To preheat this condensate, the purpose of preheating the condensate is to increase the temperature of the feed water. Indirectly, by regeneration mechanism or feed water heating mechanism, we are going to increase the temperature of the feed water. Once the high temperature feed water can be allowed to the boiler, definitely heat input is decreasing. Because of the decrease in heat input, definitely thermal efficiency is going to increase. Anyhow, so this condensate, for the purpose of preheating the condensate, what we are doing is, we are connecting a heat exchanger somewhere here, that is called feed water heater. For that feed water heater, right, condensate is allowed. For increasing the temperature of the condensate, we are extracting a part of the steam. We are extracting a part of the steam from the lateral stages of the turbine. That mechanism is called bleeding. That steam is called blood steam. That blood steam is going to directly mix with the condensate. By the time the blood steam is condensing in the condensate, that is the liquid, the blood steam is losing the latent heat. The latent heat lost by the blood steam is received by the condensate, but the condensate is receiving the same amount of heat as a sensible heat, therefore condensate temperature is going to increase. And on the other hand, by the time the blood stream is losing the latent heat, it cannot drop the temperature because latent heat is happening at constant temperature. It means whatever the latent heat which is dumped to the condensate is receiving the latent heat dumped by the blood stream as a sensible heat. Because of that, the temperature of the condensate increases. The same condensate at the inlet of the boiler is called feed water. With this arrangement, the feed water temperature is going to increase. Once the feed water temperature is increasing, the heat input to the boiler is decreasing. Therefore, thermal efficiency increases. So, this kind of mechanism is called regeneration mechanism. That regeneration mechanism is obtained by extracting a part of the steam from the lateral part of the turbine. Dear friends, remember, wherever you go for regeneration, that is either gas turbine power plant or steam turbine power plant, the efficiency always increasing. Okay? Anyhow, look at the options, right? In a steam power plant, feed water heater is a heat exchanger to preheat the feed water by extracting the steam from lateral stages of the turbine. Option D is absolutely correct. Okay? Similarly, look at the another important question. Ask like this. Reheating in a gas turbine. Reheating for the gas turbine, main intention is to increase the turbine work output. Once again, reheating mechanism is not only used for gas turbine power plant but also used for steam turbine power plant. But the intention of the reheating for both gas turbine power plant and steam turbine power plant is not same. The intention of the reheating for the gas turbine power plant is for increasing the turbine work output or turbine work, whereas the main intention of the reheating of the steam for the steam turbine power plant is to minimize the moisture content in the lateral stages of the turbine for increasing the life of the turbine. Of course, with reheating mechanism in the steam turbine power plant, the turbine work may be increasing, but that is not main intention for the steam turbine power plant reheating. Once again, the main intention of the reheating of the steam in the steam turbine power plant to decrease the moisture content in the lateral part of the turbine, steam turbine. Whereas for the gas turbine, the main intention of the reheating is to increase the turbine output or turbine work. Look at the options. Reheating in a gas turbine increases the turbine work. Option C is absolutely correct. Okay. Similarly, look at the another question. It is asked like this. The ideal gas refrigeration cycle is the same as the Brayton cycle? No, Brayton cycle is the critical cycle for gas turbine power plant. Of course, Brayton cycle is also called Joule cycle. Remember it, Joule cycle. Reversed Brayton cycle, yes, reversed Brayton cycle, another name is Bell-Coleman cycle. Bell-Coleman cycle is for refrigeration. The Bell-Coleman cycle is coming under reversed Brayton cycle, which is used as a gas refrigeration cycle or air refrigeration system. That means for Bell-Coleman cycle, gas or ideal gas or atmospheric air is the working material or refrigerant. Anyhow, the ideal gas refrigeration cycle is the same as the reversed Brayton cycle, is also called Bell-Coleman cycle. Option B is absolutely correct. Okay. Similarly, look at the another question. It is asked like this. A refrigerator operating on reversed Carnot cycle extracts 500 kilojoules per minute. That means refrigeration effect. Refrigeration effect is given 500 kilojoules per minute. Heat from a refrigerated space being maintained at minus 16 degrees centigrade. That means minimum temperature maintained or the temperature where the refrigeration effect is happening is minus 16 degrees centigrade. It is equal to minus 16 plus 273. 273. Simplify this value for getting 257 Kelvin. And rejected heat to the atmosphere at 27 degrees centigrade. The temperature where the heat is rejected, that I am marking as maximum temperature, is atmospheric temperature 27 degrees centigrade. 27 plus 273, I am directly writing 300 Kelvin. What is the work input required to run the refrigerator? You are asked to decide the work input to the refrigerator. For that, so this is the refrigerator. This refrigerator is receiving the heat from the cold source or the place where the working stuff is cooled, and it is rejecting heat to the atmosphere. The amount of heat absorption Q1 is equal to refrigeration effect. That refrigeration effect is given 500 kilojoules per minute. But refrigerator is coming under work consuming device. By consuming the work, it is extracting the heat from the cold source, is maintaining T1 temperature. That T1 I wrote as a minimum temperature 257 Kelvin, 257 Kelvin, and it is rejecting the heat to atmosphere, that is the Tmax, that I am marking as T2. Here atmosphere temperature is Tmax, that is marked as T2, 300 Kelvin. 300 Kelvin. You are asked to find what is the work input for the system. Very simple. The COP of the refrigerator, COP of the refrigerator equal to refrigeration effect dividing by work input. If it is operating between the two temperature limits with all reversible process, it must be equal to minimum temperature by maximum temperature minus minimum temperature. Minimum temperature. A refrigeration effect, how much it is given? 500. 500 divided by work input equal to minimum temperature. This is the minimum temperature, T minimum, and this is the maximum temperature, T maximum. T minimum is 275 dividing by maximum 275 or 257. 1 minute. It is 257. 1 minute. Should be very careful. Minus 16 plus 273. 257 Kelvin. 257 Kelvin. 257 Kelvin, yes. 257, should be very careful while we are discussing in the limited space. 257 dividing by T maximum equal to 300 minus 257. Simplify this value for getting the work input. Here work input equal to 500 into 300 minus 257 dividing by 257. Simplify this value for getting around 83.6 kilojoules per minute. That is the work input required for this refrigerator, 83.6. Look at the option D. Option D is absolutely correct. Okay, it is also most expected question. I can say 5-star question. Here 5-star question means the most expected question. Okay, similarly look at the another important question. Ask like this: a cold storage is to be maintained at minus 5 degrees centigrade. The cold storage is maintaining minus 5 degrees centigrade. That is the minimum temperature. That minimum temperature is minus 5 plus 273 is equal to 268 Kelvin. While the surroundings are at 35 degrees centigrade. Surrounding temperature that I am marking as maximum temperature 35 plus 273 is equal to 308 Kelvin. That is the maximum temperature. The heat leakage from the surroundings into the cold storage is estimated to be 29 kilowatts. That means the amount of heat leaking. Let us take the cold storage. This is the cold storage. For this cold storage, continuously heat is leaking. How much is leaking? 29 kilowatts. 29 kilowatts. If this much amount of heat is leaked into the cold storage, you cannot maintain the required temperature, that is minus 5 degrees centigrade. It means whatever the heat which is leaked into the cold storage, that must be removed. Right? How much amount of heat to be removed? The same amount to maintain the same temperature, 29 kilowatts. Therefore, this 29 kilowatts itself is the refrigeration effect. Whatever the heat which is leaked into the cold storage, that must be removed to maintain the constant temperature. Right? Therefore, this is the refrigeration effect. So, anyhow, refrigeration effect is given indirectly equal to 29 kilowatts. The actual COP of the refrigeration plant used is 1/3 of the ideal plant working between the same temperatures. The power required to drive the plant will be. That means the actual COP equal to 1/3 of the ideal COP or theoretical COP. Then you are asked to decide power input to the system. Right? For that, the actual COP actual COP must be equal to refrigeration effect by power input or work input, power input. This actual COP is given 1/3 of the ideal COP, 1/3 of the ideal COP equal to refrigeration effect dividing by power. The ideal COP, 1/3, ideal COP is what? T minimum by T maximum minus T minimum. It must be equal to refrigeration effect dividing by power. 1/3, what is the T minimum? T minimum is 268 Kelvin, 268 Kelvin dividing by T maximum 308, 308 minus 268. It must be equal to refrigeration effect. What is the refrigeration effect? 29 dividing by power. From this you can decide the power. Simplify this value for getting the power around 12.9 kilowatts. That is the amount of power required for this refrigerator. Therefore, 12.9 you can select the option D, 12.9. It is very close to 13 kilowatts. 12 also given, but 12 is not correct. It is 12.9, very close to 13. Therefore, option D is absolutely correct. Okay. It is also most expected question. I can say 5-star question. Most expected question for the competitive exams. Similarly, look at the last question. Right? Last question is asked like this. The following data refers to compression refrigerator enthalpy at constant enthalpy at compression inlet 1200 kilojoules per kg, enthalpy at compressor outlet 1400 kilojoules per kg, enthalpy at condenser outlet 200 kilojoules per kg, the COP of the refrigerator. Let us draw the pressure versus enthalpy diagram. Pressure versus enthalpy. This is the saturation dome. The vapor compression refrigeration system has only two pressure limits. Pressure before compression is P1, pressure after compression is P2. Let us say ideal vapor compression refrigerant system. Ideal vapor compression refrigerant system means the refrigerant is entering to compressor with P1 pressure under saturated vapor state. That means you try to mark the state 1 along the saturated vapor curve where that curve is meeting the P1, that is the state 1, is representing the beginning of the compression. 1 to 2 is the compression process, 2 to 3 is the condensation process, 3 to 4 is the throttling process or isenthalpic process, 4 to 1 is the evaporation process. Now let me mark the notations. Here 1 to 2 is the compression process, 2 to 3 condensation process, 3 to 4 throttling process, 4 to 1 evaporation process. Look at the enthalpy limits. Enthalpy limits are H1 be the enthalpy of the refrigerant before compression, H2 be the enthalpy of the refrigerant after compression. Of course, H4 equal to H3. That is the enthalpy after throttling equal to enthalpy before throttling. Enthalpy before throttling means enthalpy at the end of the condensation process. Now look at the enthalpy is given. Enthalpy is given are the following data refers to compression refrigerator. Enthalpy of the refrigerant at the compression inlet 1200 kilojoules per kg. It is 1200 kilojoules per kg. H2 is given 1400. Enthalpy after condensation 200. This is 200 kilojoules per kg. Then what is the COP? COP equal to refrigeration effect dividing by work input. A refrigeration effect is taking place in the process 4-1. That refrigeration effect equal to enthalpy after evaporator minus enthalpy before evaporator, H1 minus H4 dividing by work input equal to enthalpy gain of the refrigerant during the compression process, that is H2 minus H1. H1 how much? 1200 dividing minus H4 is 200 dividing by H2 1400 minus 1200. Simplify this value. It is 1000 dividing by 200 is equal to 5. That is the COP of the compression difference system or vapor compression difference system. Option C is absolutely correct. Okay, it is also most expected question, then I can say it is the 5-star question. Okay, so with this, right, so I am concluding this session. In the next session, we will discuss the syllabus and most expected questions from the power plant engineering and internal combustion engines. Okay, so with this, my dear students, I am concluding this session. I hope all of you clearly understood all the important questions what we discussed. Understood or not? Yes. Have a great day.